Hello and welcome to another GCSE revision video, and in this video we're going to be looking at the pyramid. Now there are many types of shapes that all are called pyramid, and here's two of them. The first one is called a triangle based pyramid or tetrahedron, and the other is a square based pyramid or pentahedron. In fact, there are many kinds of pyramid, but all pyramids have a base which can be any two-dimensional shape and a triangle coming from each of the edges of that one shape, where one vertex of every triangle meet together at a single point called an apex. Regardless of the shape of the base, however, the surface area of the pyramid is simply the sum of the areas of each individual face. Just remember to include the base as one of those faces. The volume of any pyramid is 1/3 of the area of the base times the perpendicular height. And you may need to use some trigonometry to find the perpendicular height. And that's basically all there is for pyramids. Let's take a practice question and see if we can put this into practice. A regular tetrahedron is made from 4 congruent equilateral triangles. In fact, it's a very special shape. It's called a Platonic solid, or one of the Platonic solids. And if one of the edges is called L, what is the surface area and volume of the pyramid in terms of L? Okay, if you want to have a crack at that by yourself, why don't you pause the video, test how good you are at it, and when you're ready for the answer, just press play. Okay, wasn't that an absolute stinker? If you managed to persevere with that question and actually come up with the answer, I just want to take my hat off to you, because that was really hard and you've done really well to do it. So even though at GCSE level you are fully equipped to answer this kind of question, it is extremely laborious maths that requires the ability to visualize the three-dimensional object, and it pulls together quite a lot of areas from the GCSE syllabus, including combining fractions, surds, trigonometry, your unit circle, and properties of an equilateral triangle, and so on. So there's quite a lot to actually take in. So well done, very well done. If you managed to do this, you should give yourself a real big pat on the back. Alright, let's get the easier stuff out the way first. We'll start with the surface area. So the surface area of the regular tetrahedron, remember the regular tetrahedron is made up of 4 equilateral triangles, all of length L. So let's quickly draw an equilateral triangle. So each length is L, and because it's an equilateral triangle, we know that all 3 angles are the same, and therefore, and since they all add up to 180 degrees, they must all be 60 degrees. Now we also know that the area of a triangle is just a half AB sine C, so that's a half of L times sine 60 degrees. Now we could have split the triangle in 2 and said half base times height, which is the hard way of doing it. You could have done that with your trigonometry, but a half L times sine 60 is definitely the easier way to do it. Now we know from our unit circle that sine 60 degrees is root 3/2, So this is 1/2 times L squared times root 3 over 2, which is equal to L squared, that's a 2, L squared root 3 over 4. So that's the area of one of the faces. So all four faces, the surface area is equal to 4L squared root 3 over 4. The 4's cancel, leaving us with L squared root 3. So that's the surface area of the regular tetrahedron, is just L squared root 3. Now for the volume I'm going to need the area of one of the faces, because the volume is equal to 1/3 the area of one of the base times the perpendicular height. Now we know the area, we just calculated that, that's L squared root 3 over 4. So I'm going to keep that and only that to try and save some space. So let's just make this clear. So the volume is equal to 1/3 the area, which is L squared root 3 over 4, and that's times the height. Okay, so what's the height? Well, the height is the shortest distance between the apex of the tetrahedron or pyramid and the base. This is true for all pyramids. The height is the shortest distance between the apex and the base. So this is this straight line going straight through the whole pyramid. In fact, I'll draw that underneath the pyramid here. It's the actual height from the base to the apex of the pyramid. Now, if I try and draw the base of the pyramid, so this is the shape I'm going to draw, is the base here of the pyramid. Now this is an equilateral triangle, so I'm going to draw the equilateral triangle here. Okay, so first of all, what do we know about the equilateral triangle? We know that all the lengths are L, and we know that all the angles are 60 degrees. So that's 60 degrees, and that's 60 degrees. And we know that this height, or the height of the whole pyramid, hits the centre of the pyramid, the exact centre of the pyramid. It's where all these lines intersect. So if we draw a line bisecting the angle of each vertex, that will bisect this line and turn it into L over 2. And this length will be L over 2. And then we can bisect this one as well. So each of these 60-degree angles have now been split into two 30-degree angles, and these lengths are L over 2. And then one more. So that means this is L over 2, and this is L over 2. And so this is the point on the base of the pyramid where the perpendicular height touches the base of the pyramid. So that's this dot here, will be this dot here. Okay, so we still need this height, h. Now if I take this line here, it can be any line from the vertex to the midpoint. It can be any of these three lines. So that will be one of these three lines. It can be any one of them. They will all be the same. I know they don't look the same length, but that's because of the perspective on the three-dimensional object. But any length from the center of the triangle to the vertex. So, and I'm going to call that length x. So that will also be x, and that will also be x. And so that's this length here, from the center to the vertex. From the center to the vertex is x, and from the center to the vertex is x. And that length is perpendicular to the height. So I can construct a right angled triangle here. So this is my length x. And so the hypotenuse of this right angled triangle would be this length here, or this length here, or this length here, depending on which vertex I'm going out to. And since they're all x, and these are all L, so that length is L, that length is L, that length is L. So this hypotenuse is L. In fact, that's the only one we actually know. Okay, so how do we find this x? Well, we have this length, L over 2. What we can do is find this length here. I'm going to call it y, just because I called this x. Now, this angle here has cut this 60 degrees in half, so this angle here is 30 degrees. And I can say that y, that's this length here, which is the opposite, divided by this L over 2, which is the adjacent. Opposite over adjacent is equal to tan theta, and this is tan 30 degrees. So this is tan 30 degrees. Okay, so I suppose the next thing to do is to find tan 30 degrees. Well, we know from our trigonometric identities that tan 30 degrees is equal to sine 30 degrees over cosine 30 degrees. And we know from our unit circle that sine 30 degrees is 1/2 and cosine 30 degrees is root 3 over 2. Okay, so y over L over 2 is equal to, well, 1/2 divided by root 3 over 2 is the same as 1/2 times 2 over root 3. So that's 1/2 times 2 over root 3. Because to divide fractions we just invert and multiply. So that's equal to 2 over 2 root 3. and we can cancel the 2's, so that's just 1 over root 3. So y over L over 2 is equal to 1 over root 3. So if we multiply both sides by L over 2, we can say y is equal to L over 2 multiplied by 1 over root 3. So therefore y is equal to 1 over 2 root 3. Okay, we can now put that information here in our y. So if I zoom in, and I can write really small and try and write a bit neater than I normally do. So this is L over 2 root 3. Okay, we're making progress. Let's go back. So now that I've got my y, I'm going to get rid of these calculations because they're just taking up space. And that just creates some space for me. Alright, so I've got my opposite, I've got my adjacent, I can find my hypotenuse now. I can just use Pythagoras theorem. So x squared is equal to y squared, which is 1 over 2 root 3 squared. Sorry, L over 2 root 3, sorry, not 1. That's what you get for writing a lowercase l that looks like a 1. L over 2 root 3 squared plus, and then this is just L over 2 squared, because this is a right angle. Okay, so squaring these is a piece of cake, so x squared is equal to L squared over 4 times 3. 2 squared is 4, root 3 squared is 3. And then that's plus, and then L squared is L squared over 2 squared, which is 4. Okay, so that 4 times 3 just becomes 12. Now if I multiply top and bottom by 3, so this becomes 3L squared divided by 4 times 3, which is 12. Then I can combine the fraction easy enough. So that's just 4L squared over 12. I can now cancel the 4 from top and bottom, so that's just L squared over 3. So if x squared is L squared over 3, then x is equal to the square root of L squared over 3. Well, the square root of L squared is L divided by the square root of 3. I can now change my x here for L over root 3. Which more importantly means that this x here, we now know this length is L over root 3. And look, we now have 2 lengths of a right angled triangle, so we can finally get the height of the actual tetrahedron. Again, so we're just using Pythagoras' theorem. So h squared is equal to L squared minus L over root 3 squared. So the height squared is equal to L squared minus L squared over 3. So if I times top and bottom by 3, I can make the denominators the same, so I can combine them. So h squared is equal to 3l squared minus l squared all over 3, which is equal to 2l squared over 3. So h is equal to the square root of all that, so that's root 2 times L over root 3. And that can go in place of the h that we've got for our formula. And now we can calculate the volume of the pyramid finally. In fact, we don't need that anymore either. So the volume of the pyramid is just 1/3 times L squared root 3 over 4 times root 2 L over root 3. So multiplying tops and bottoms, because that's just how you multiply fractions, is just multiply the numerators and denominators. 1 times L squared times root 3 is L squared root 3. And times root 2 times L, so that L squared will become L cubed, and then we times by root 2, and then we divide that by root 3 times 4 times 3, so that's 12 root 3. Root 3's cancel, and so the volume of a regular tetrahedron is L cubed root 2 over 12. If you manage to get that, you deserve a big pat on the back. Congratulations, that's absolutely amazing, because that was really hard work. Okay, if you're studying for your GCSEs this year, I'd like to wish you all the best with your revision and all the best with your exams. If you liked this video, click the like button, and click the like button as well if you want to see more of the same. Hit that subscribe button if you want to be notified when the videos come out, and turn the notifications on. And use the comments section if you have any suggestions for any GCSE maths revision videos that you would like to see me cover. Okay, have a good day, and I'll look forward to seeing you in another video.